Well, I start recording, okay, and we start our discussion. Well, today we need to finish our discussion of quantum dynamics. Yep. So on our previous talk, previous meeting, we discussed the Schrödinger picture. Yes. So the Schrödinger picture is a story about evolution of some quantum state with some Hamiltonian, and so the basic equation, as you remember, was this this I d over dt, this psi of t, yep, and with some Hamiltonian, and in general case, this Hamiltonian depends on time, yes. In this handwritten version of notes, I add this link on a PDF with the derivation of this time-ordered exponent. So actually, this stuff. Yes. So if you are interested in explicit derivation, you can look. It's really nice. Well, and before we proceed to Heisenberg picture, I would like to note that actually, so what we know that the solution of our Schrödinger equation is given by what we call this evolution operator. Yes. So we need to act on an initial state in order to obtain our vector at some time t, and what we see is that actually we can take this form and put it back into Schrödinger equation, and then we obtain such a construction in this form. So we have this derivative. Here we have our our Schrödinger equation, and here we have this this unitary operator which acts on initial state, and you see that this equation is true, yes, because we just substituted solution back to equation, and you see that it's true for every psi naught, yes, for every initial state, and so we can remove this this psi naught and come to the equation on a unitary operator. So you see that we can think about Schrödinger equation as equation on evolution operator. Yes, so it looks a bit strange, but nevertheless, sometimes it's very important. Actually, this time-ordered exponent actually derived using this expression. And you see that for time equal to 0, we have that our so the initial condition on our unitary evolution operator is given by this expression. So at initial time, it's time equal to 0 is just identity operator. Yes, quite trivial fact. Okay, so then let us move to our Heisenberg picture. So I think most of you already know what it is, but nevertheless, let us revise this story. So what we have. We have our Schrödinger picture, yes, and we can think about some probability to obtain some measurement outcome for some state at some time, yes. And this expression to this probability of obtaining some outcome will be given by this expression. So what we have, so here we have our state at time t, yes. So I just take my initial state or not and put it in the sandwich of this evolution operators, yes. And this is rho t for in the Schrödinger picture, and this projector p is projector which describes this outcome, yes. And so what we can do, we can take this unitary operator and just move it in the trace. Yes, and what we come to this form, and we can take this expression, take this construction, and say that okay, actually our initial state is the same, but what evolves is actually not our state, but our operator, and this is what is called a Heisenberg picture. Yes, so we say that our operator evolves, and the results of the evolution given by this expression. Note that here we have this dagger on the first position and the operator without dagger on the right hand side. Okay, and again we have some initial condition on our evolving operator in this case, yes, and it's given by the operator from Schrödinger picture. So again, so the operator at time t in the Heisenberg picture coincides with the operator from the Schrödinger picture. Yep. So because here I consider some probability of some outcome because it's what's we're interested in. But actually, so next we will see that we can generalize it to a whole operator. What is also important that in general, actually, even in a Schrödinger picture, our operator can depend on time. So the way how you can think about it, for example, I think about it in the following way: that okay, imagine that you have some measurement device, and it evolves in some sense. So, for example, for different times, you measure different projections on different axes. Yes. So even in Schrödinger picture, your operator can depend on time, and it's okay. Yes. And if we would like to derive this the equation on the evolution in Heisenberg picture, so we can just take its derivative. So let me move this derivation. So what we have? Yep. So we just take our projector. Yes, we consider it in the Schrödinger picture. So H here is again. So it's Heisenberg picture. Yes, and we know that we know how it's constructed. Yes. So note that here we have this projector which can also depend on time, but it's come from Schrödinger picture. Yes, and then we take this derivative, and we have the three terms, and so we need to consider derivatives for all three terms. Yes, and what we can use these two expressions. So we know what is derivative of our evolution operator. We can consider its adjoint, yes, and come to the evolution of its Hermitian adjoint. Yes, and we just take derivatives of all three parts of our construction, and we come to three terms. So this is the first term. Yes. So again, this H is Hamiltonian. Yes, it's Hermitian operator, and then it was the derivative of this U plus. Yes. Then we take the derivative of our central operator. Yes, and so we come to this construction. So here is this derivative of our Schrödinger operator. Yes. In this sandwich of this evolution operators, and usually people write it like this, so it's just like convention. Yes, that so it's like partial derivative. Yes, and finally the third term corresponds to derivative of this of the third operator. Yes, and you see that unfortunately, if our Hamiltonian is time dependent, then in general case, actually, you do not have that your Hamiltonian and your unitary operator at some time t, and your Hamiltonian actually they may not commute. Again, it's okay in general. Yes, and so in this case, what we obtain, we come to this not very nice expression. So you see that we have this sandwich of this unitary evolution operators, and inside the sandwich we have a commutator, because its commutator composed from the first term and the last term, and here we have this minus. This is why we obtain this commutator. Yes, and so it's not very nice, but nevertheless it's what actually happens. And finally we have this term which corresponds to the derivative of our Schrödinger, or derivative of the Schrödinger operator in the Schrödinger picture. Yes, The good picture appears if we sorry. So if our Hamiltonian is time independent, it's always, as usual, more convenient case. Yes. Oh, sorry. Let me move it here. So if our Hamiltonian is time independent, then we have a commutation. Then our commutator of our Hamiltonian and evolution operator equal to 0. Yep. And in this case, we can move our Hamiltonian over these evolution operators in our two terms. And finally, what we come to this very, I think, known expression, yes, for a derivative of our Heisenberg, of our operator in the Heisenberg picture. Yes, so this is this commutator, yes, and this term which corresponds to, again, to this partial derivative. Yes, and this is what people usually think about when they speak about this Heisenberg picture. Well, so here we consider this P again. It was our just projector, yes. So it was a part of some operator, and you see that it's this. So this story can be generalized to a full operator. So we can consider a full observable, not only term it's in its spectral decomposition, but again the full operator, which consists of a number of different projectors with some eigenvalues. Yes, and again we can consider its Hermitian. We can consider its operator in the Heisenberg picture, and in the case of where Hamiltonian does not depend on time, so then we come to this expression. So here is this derivative of full operator, and here we have again this partial derivative. And note that actually in general case we can have both this dependence of this projectors and this eigenvalues in our full operator, and so in this case we consider this full derivative. Okay, and again, so the initial state of the initial operator in the Heisenberg picture coincides with the operator in the Schrödinger picture. Yes, so it's quite usual story. So any questions on this? It's okay, yeah. Yep. Sorry, where? Where we? Yep. So once again, so this is where we obtain this form of this derivative. We obtain it from a Schrödinger picture, so from a Schrödinger equation. So we start from a Schrödinger equation. We say, okay, we have this one, then we put inside, and we come to this. So okay, so we have this ht or dt. So we have this h. No, okay. So actually, so if h depends on t, here I do not have this expression. I have this huge time order exponent, and so. But nevertheless, this story is always true. Any questions? No. Okay. Well, and final stories on this evolution pictures. It's also well known. I hope. The well-known story about what is called Dirac picture or interaction picture. So let me copy it from the basic notes. So so this what is called interaction picture. Sometimes it's called. So it's a story where our Hamiltonian have two parts. Here I denote it with H1 and H2. And H1 should be time independent, and we will use this H1 in order to construct, let's say, this Heisenberg picture. And we use H2, which generally can depend on time. We use it in order to construct, let's say, Schrödinger picture. And so what we know that we may start with the Schrödinger picture, yes, where we have a full solution psi, which evolution governed by the full Hamiltonian. And then let us introduce new player, this psi interaction, psi int. So this is just so what we have. We take our full solution, our really true solution, and we in some sense we remove its evolution which governed by H1. So you may think as so we have these two parts of our Hamiltonian, and let's say we have H1 is some basic part, H2 is some addition. And we would like to study not the full evolution, but we would like to study, let's say, response on of our system only on this H2 part. And in order to do so, we like what people sometimes say we move into rotating frame, which rotates with this H1 Hamiltonian. So so we consider this psi interaction. This state, and we just can consider its equation, its evolution. So we can just consider its time derivative, and if we consider its time derivative, so we just compute its derivative. Yes, and here we have dependence of let's say, let me use another color. So we have dependence here, we have dependence here. So there are two terms. And if we consider a derivative with respect to H1, so we have this additional I here, I have this I here, and if we consider the derivative of the second part, so we have this. So the derivative will gives us this H1 plus H2, yes, and if we remove this bracket, so we see that two parts of this two terms will cancel each other, and finally we come to this construction where we introduce additional identity operator. Yes, and we take we take this construction and denote it with some VT. And we see that this construction gives me back this psi interaction. And we're interested in this psi interaction because we started from a derivative of psi interaction. So finally, we come to this expression. Yes. So we see that so our psi interaction evolves like in the Schrödinger picture. However, the effective Hamiltonian, which of course in its core it has this H2, but this Hamiltonian is not H2, but it's like corrected version of a H2. Yes, and it's given by this. So we need to put the sandwich of these H1s. So it's like H2 in the rotated frame of H1. Yes. So you need to take into account. So for example, if H2 commutes with H1, then it's okay. Then these two terms will cancel each other. Yes, but in general case, H2 and H1 they do not commute. So we need to consider this construction. So this form. Yes, and actually it appears that it's quite useful thing. As far as I know, so Alexey Fedorov will show you, or maybe already shown you, how to derive Rabi oscillations with this rotative value approximation. So you already consider it, yes? So where this Rabi pulses, this Rabi oscillations come from? So do you consider it, this story?
Wait. Yeah, are you talking about lectures which disappeared today because Yoshi is apparently
busy? Okay. So the story was that we have this the first term H omega times sigma z, which corresponds, let's say 1/2, which corresponds to some basic Hamiltonian of two-level system. Yes, and then we have this additional term with some electric field which acts on our two-level system, and the operator which is proportional to sigma x. Yes, and if you consider such a Hamiltonian, unfortunately, you cannot solve it because there is time dependence here. And this is some field which oscillates with some other frequency, let's say omega naught. Yes, and so in general, you cannot solve it, unfortunately. But if you go to this rotating frame, you will see that so you appear, so your operator V also appears to be time dependent. However, there are two kinds of terms, and there is time independent part and the part which oscillates with double frequency. And usually people say, okay, so it's fastly oscillating term, so we can neglect it. And so we come to psi, to this V, which does not depend on time, and then we come to these Rabi oscillations. So I hope so you will consider it. Okay, so nevertheless, so on this Dirac picture, some questions. So it's quite known stuff for you. So silence in the audience. Well, okay. I hope it's okay. Well, so the section 1.5, I called it entanglement, and probably I hope it will be more let's say new for you. Yes, and so we will speak about entanglement, and we will start with some basic thing which is called Schmidt decomposition. It's very fundamental stuff in quantum information. Yes, and the story is the following. So let us consider two objects, two particles, for example. Yes. Object A and object B, and let's say them live in two Hilbert spaces, and let us have two orthonormal bases, which I denote with E and H. Okay, so dimensions of the spaces can be different. It's okay, and let us consider some general state, some general pure state, which lives in the space of tensor product. So it's some pure state of this composite system, yes, NB. And you see that, so in general, it can be described in this form. So I have my basis vectors, yes, and I have some coefficients, some complex coefficients. And of course, the sum of these all coefficients, modulo square, is equal to 1, as usual. Okay, it's quite standard thing. And then let us consider a partial reduced state of our composite system. So let us consider the state of particle A. Yes, and as we already know, the state of this particle can be obtained by taking this partial trace over the other system, over the B system. Yes, and if I consider this trace, what I obtain, so I should take my psi's, put it in this expression, and here I come to this summation. Yes, so I have already 4 indices, so 2 from one psi, 2 from other psi. Yes, and I should take my partial trace over B system. Yes, and you see that when I will take this partial trace, the only terms which will survive is the terms where this G is equal to L. Yes. And finally, I come to this expression. So I have this summation. So these indices are the same, yes, because they survived after this partial trace. And here is summation. So here is this projectors in the space of A system, yes. And of course, so I have this matrix, and I always can consider its spectral decomposition. So I can find some state phi, yes, which diagonalize my system. Yes, so I obtain this diagonal form with respect to this phi i's. Okay, and I know that this phi I, so since rho A is a Hermitian operator, this phi I, they corresponds to some orthonormal basis. So I can use this orthonormal basis in order to describe my system in A space. Yes, and I can just take my original state psi and rewrite it in a new basis, where the basis in the space A, yes, will be my vectors, which comes from this diagonalization of my first system for A. Yeah. So let me move it here. So we take this phi I, yes, as a basis, and we write our psi, where we have this phi I in a system. And you see that, of course, these coefficients will be not C, but some D. Yes. And what I consider here, I take this each of these phi I over, let's say, over the bracket, and introduce new vector. I denote it with he I, and actually, so he I is just summation over all the states IHG times this coefficients. Okay, and you see that, of course, this he it's not the set of the states he I, it's just some states. Yes, and so I cannot, so for now I cannot say nothing about their normalization, so either they are orthogonal or orthonormal and so on. So and okay, I can imagine that I think that they are not at least normalized. Yes. Okay, and so we consider this form, and let us compute the density matrix of our state A, of our particle A once again. So with respect to this new form. Yes. So what I take, I just take my new form, yes, and just write its partial trace, yes, as usual. And what we obtain. So again, I have this summation over number of indices. So here I have this phi I, phi j, and so I take this partial trace over B system. Yes, also here I have this H case. Yes, so which come from this partial trace, and inside I have this he I and he j, which comes from this psi. Yeah. And you see that so I have these two terms, and I can swap them. Yes, and see that so here I have summation over OK, and the summation of this H case is just identity operator. Yes, so what I come to, it's just the product of he j times he I. Yep. And so I obtain this construction. Yes. And then I remember, I say, well, wait a minute, but I remember that my state of my particle A was this with this diagonal form. Yes. And I look at them and just compare them. And what I see, so I see that so they should coincide. So, and from this identity, I can conclude that my state he j and he I should be orthogonal to each other. Yes, in order to remove terms where I does not equal to j. Yep. And what I obtain this. I obtain this picture. So what I know. So I know that my he j times he I should be equal to pi I times Kronecker symbol. Yes, at least for this indices I, which goes from 1 to rank rho A. So it comes from the fact that actually my state rho A, it cannot be like full rank. Yes, so I have some rho A, and then have some non-zero coefficients. Yes. And then I have zeros. Yes, and this will, the number of these non-zero coefficients will give me the rank of my matrix. Yes. So and for this at least for these i's which are from 1 to rank of my matrix, I have this identity, and for all others, I do not have. So here I have the zeros. Yes. And this corresponds to the fact that my he I times he I should be equal to 0. And from the rules of tensor of scalar product, we know that if a scalar product of a vector times itself is equal to 0, so the only case where it can happen is where this vector is equal to 0. Yes. So I understand that my he I, where I is larger than my rank, so it's just equal to 0. Okay. And then what I can consider. So I take my so I divide the previous equation. So this previous story, I divide it over pi. So I remove it, let's say, from here. Yes, and I consider it as a sum of 1 square root pi, 1 square root pi, and I denote this product or as of 1 over square root of pi by hi so I denote it by this hi with a tilde. And so the idea is that what I would like to obtain, I would like to obtain that I would like to obtain a set of vectors which I denote with this hi tilde in such a way that it's already orthonormal. Yes, so I know that they are orthogonal to each other already, and after dividing by square root of pi, I obtain this. They are not only orthogonal, but they only so they make this orthonormal set. Yes, and and finally, what I come to this final representation of my state, which what is called Schmidt decomposition. So let me move it here up. So what is a Schmidt decomposition? It's yep. So Schmidt decomposition is a representation of my state in this form. So what we see here. So the basic idea is that, okay, I have two sets of orthonormal states in two spaces, yes? And here I consider a summation where I have a same index. So I have on the single index I, and I obtain my state in this form where I have, so I take a vector from one space, vector from other space, multiplied by some coefficients, and another vector from one space, another vector from other space, multiplied by some coefficients, so on. And so again, so the basic idea is that here I have summation with only one index. So in contrast to the original representation of this psi, yes, where I have summation over two indices. So this is the basic difference, okay? And and you see that the summation here goes from 1 to rank of my reduced density matrix, rho A. Yes. So the number of coefficients in this Schmidt decomposition cannot be larger than the rank of one of two reduced density matrices. And okay, and this is what is called Schmidt decomposition. And actually, you can see that it's not unique in a sense that I always can introduce some. So I can put this scale, this exponent I, some theta I, with minus and without minus. And I can put those exponents like inside this basis vectors, and so I obtain some change into my basis vectors. But the whole picture will remain to be true. Yes. So you can see in some sense there is a number of different Schmidt decompositions, but so they are quite similar because there's only these phase factors changes. Okay. And another important like object is what is called a Schmidt rank, and Schmidt rank is just a number of terms in Schmidt decomposition. So a number of these non-zero elements in our Schmidt decomposition, yes, and it's important that actually I write it here. So we have these properties that let me move it here. So our Schmidt rank cannot be larger than the minimal dimension of two subsystems. Yes, because you see that we have this summation over rank where I goes from 1 to rank of two subsystem of my first subsystem, but they like symmetrical in respect that we can do it with respect to the one subsystem or another subsystem. And so the Schmidt rank cannot be larger than the dimension of the minimum of two dimensions. Yes. So it's important, for example, in the case where, for example, you have two-level system, like two-level atom, yes, and you have the mode of electromagnetic field, or even a bath of electromagnetic, of different like bosonic buses. Yes, so you have a number of, like say, oscillators, and you have your composite system in some state psi. Yes, and Schmidt decomposition says you that any state of your composite system of your atom and a number of fields with which is infinite dimension each, yes, it always can be decomposed into sum of two terms. Yes, like C1 times, I don't know, like C1 phi 1 plus C2 times psi2 phi 2. Yes, where psi 1, psi 2 is states of atom, some orthogonal states of atom, and phi 1 and phi 2 maybe some complex, but nevertheless some are two orthogonal states of these bosons. Yes, of this Bass infinite dimension. Yes, and sometimes it's quite useful. Yes, and the second point here is that from the Smith decomposition, you can see that if you consider your reduced states of your A system and your B system, yes, you will see that actually, so your state of your A system is given by this PIs times this phi, yes, and similarly your reduced state of your B system is given by the same PIs times this HIs, so the states from your second subsystem, and you see that these two states have the same spectrum always. Yes, so the spectrum of your reduced states is given by these coefficients PI, and they're always the same. And also it's quite interesting story. So you can consider some let's say very large system with a number of particles, whatever. Yes. And if you know that your system is in some pure state, yes, and you can divide your system as you want, like this one, yes, in two parts, or like in this one, and you always know that the spectrum of this part of your system is the same as the spectrum of all the rest of your system. And again, it's maybe a very small, some very small state, and this may be the state of a large number of particles, but the spectrum will be the same. Yes, and it's quite important. Well, so questions on this story? Does it clear for you? So any, yep. Well, maybe what is not clear?
It's not an action, but I never worked with this, and I don't know where we should apply this exactly. Like, why is it important?
Why is it important?
Is there any examples we could use this, or is just it exists and we move on?
Maybe you should get some exercises.
Well, okay, I will think about it.
Because if it's important, then we need to.
Okay, so to feel where
if it's not, we just need to remember it.
Okay.
На самом деле, если мы подумаем про шмидтовский ранг кросс-матрицы, обязательно состояние, он часто возникает в истории, когда мы, у нас есть какой-то грид мы пытаемся его разложить на разные матрицы, количество этих разных матриц, которые мы можем его разложить, но связано с этим шмидтовским рамком. Если отойти на состояние, на просто матрицы, как бы практически пример вполне себе есть.
Ну окей, я просто штуку вижу первый раз, и типа мне еще поймет, что
она встречается в статьях, и если вы прям хорошо чувствуете, это в целом нам помогло.
Okay. So okay, so actually, so there is another.
Такой вопрос. У нас же изначально, вы говорите, что любое состояние можно так разложить, да? У нас изначально было как бы HA плюс HB степени свободы, да, где HA изначально, делает пространство первого состояния, HB, или умножить даже.
So it's a tensor product. So the whole dimension of the system is dA times dB.
И потом вы говорите, я возьму любой вектор в этой системе, и каким-то образом я его разложу по
with a number of terms, with minimum of which is not yes, so it's less or equal than this. Yes, it's a kind of.
Меньшим числом степени свободы. То есть получается, какие-то из изначальных состояний были независимыми никак.
No. So look, what is important here is that this decomposition it's unique for every state. So we do not throw away any information. It's like, okay, so
Взаимно ли однозначно эта операция для каждого состояния?
Yes.
А в обратную сторону не могу по шмидтовскому разложению восстановить?
Of course. So the point is here. So okay. So I have this like huge dimension, huge space HA times HB. Yes, and I take some vector here, some point. Yes, and I say okay. For this point, I have some nice. I can choose some nice basis inside HA and HB, and in this nice basis, my state will have this nice form. Yes. So again, so for this, for some state, for state, I have nice basis where my state has this nice form. For some, so you ask, well, but okay, so if I take some other state, yes, this other state will have this nice form, but with respect to a different basis, and of course it will have some different coefficients. Yes, so so the information will not disappear because each particle corresponds to a new basis.
So the point is that it's not like an isomorphism between the first phase and the second phase. There is not unique basis in the second phase for any point in the first phase.
Of course.
For each point there is, okay.
So it's also okay. So this story about that we always can find this basis, but this basis will be different for all different states. Okay, and another important point, I do not write it in my handwritten lectures, but I think I should write it here, like 1.2. It is what is called purification, and it's very important in purification, and it's very important in quantum cryptography. And the idea is is the following. So consider some Hilbert space H, yes, and let this I will denote it with S as some system, yes, and let this Hilbert space have some basis, again some EI, where E goes from 1 to ds, where ds is my dimension of my subsystem, and let me consider some density metrics, yes, some rho s, which will be given by some AGJ, some coefficients rho ij times EI times EJ, yes. And what I claim? I claim that for every such a density matrix, there exists at least one. Actually, it exists in an infinite number of a state psi. I will denote it as SE, such that the trace over E of this psi SE will give me rho s.
What is E?
So what is E? So E here, so I introduce some HE, where E is stands for, let's say, environment. Yes. And the dimension of this space is, let's say, I take some orthonormal basis, and the dimension of this space should be at least of rank of my rho s. Yes. So again, I have some density matrix S, rho s. Yes. And I claim that there exists some pure states which lives in some composite, it lives in the space of tensor product of my initial space HS and some additional space HE, such that the trace over this environment this additional system will give me my density matrix.
So it's the pure state, yeah?
Yes, it's pure. So that is why this procedure called purification.
Oh, okay, sorry.
So yes, so we take our mixed state and we say that it is a part. So every mixed state is a part of some pure extended of a pure state in some extended space. Yes. So the question for you: how can I derive this psi? Any ideas? So what is the form of this psi? Such that I take a partial trace over E and obtain this my rho S. So any ideas how we can construct this state? Okay, how?
So then the product of E and H.
Then the product of E and what?
H that by this environment.
Which kinds of? So okay, so which?
Maybe
И просто это было такой же.
да.
Oh, actually, yes.
Okay.
So what we can do? So first, we need to diagonalize this stuff and write it in more convenient form. Some pi's times phi. Yes, where phi is my basis, where my matrix has this diagonal form. And then what I can consider, I can consider a state in a form of I square root of pi, and here I have this phi, which lives in my S system tensor, some basis states of my second system. Yes.
Different dimensions.
Huh? So in order, so you see that the number of these terms is given by rank of your matrix. Yes, and that is why I need the dimension of my environment to be at least a rank of my system. So for example, if
But it can be bigger.
It can be bigger, yeah,
And
at least.
And what happens with the base vectors which are out of rank?
So here I have this like zeros. So in this, so I just take only first rank elements, and then
Is pi just 0 for any I bigger than rank, or what?
I do not use them. Okay, so here I just construct my state, and then I do not use any new states.
And so here we see it depends only on the system basis, but if we change the environment basis, what's happening?
Nothing. That is why a number of your purifications is infinite in some sense. So you can consider a number of different pure states, which corresponds to your mixed state.
So the dimension is of environment is bigger. I can choose any basis in any, for example, rank.
Yep. Subset.
Basis,
Yep.
Subset.
Yep. Subset. And actually, you can use. So let us maybe consider an example. So again, some general example. Let's say example. So consider our maximally entangled states. So there is a number of standard maximally entangled states. They denoted like this, square root of 1. So it's 2-qubit case, yes. So there are 2 states, phi plus minus, and 2 states psi plus minus. Oh, sorry. 0, 1 plus minus 1, 0. Yep. So this is four different states in for 2 qubits. Yep. And for each of these states, I have my rho A equal to rho B. So A, B, and just labels of my qubits. Yes. What will be the state of my reduced? What will be the reduced state of of my qubits? So I take the state of the whole system. What will be the reduced state? What do you think of A and B? Okay, so it will be your home exercise. So I will add it in the self-check assignment. So it will be just diagonal matrix. And so so it can be easily checked. Yes, and the idea is that, look, so I have my density matrix. For example, I take row A, yes, in this diagonal form. And each of these pure states, like, purify my maximal integral state. So each of these states, phi plus and phi minus, purify my maximally mixed state. So I take my row A, for example, yes, and I would like to find some pure state in AB system. So I add additional system B, and I would like that the pure state of AB system will be such that the reduced state will give me this my original density matrix. And you see that all of them, this phi plus, phi minus, psi plus, psi minus, they will give me the same reduced state. Okay, and you see actually they are orthogonal to each other. Yes, so each of these four states, if you consider its scalar product, it will give you 0. Okay. Well, so some story about definitions is the following. So first, actually this Schmidt decomposition gives you the definition of entanglement, what people call entangled state. And the idea is quite simple. So if your rank of your pure state is greater than 1, so we have at least 2 terms in your Schmidt decomposition, then the resulting state called entangled. Yes, the entangled is opposite to for separable, so it's not non-separable. Okay. So the idea is quite trivial. So what does it mean? That your Schmidt rank is larger than 1. That your decomposition looks like this. Yes, you have this C1 times some phi 1 high 1. Yes, plus C2 times phi2 he2, where both C1 and C2 are non-zero, so they are something non-zero here. And in this case, you can already say that your state cannot be decomposed in such a way. So you cannot decompose it as a tensor product of just two states. Yes, because you cannot. And so that is why. So it's not like not factorizable, and otherwise it calls entangled. Yes. Well, the second. Yep.
Calculate one, I know what is the second, so what is physical
entangled? Okay, it means that, of course, so it's pure state where you have some correlations. Where the correlations come from? Look, so you have this kind of decomposition. Yes. So okay, well, so look, yeah. So look, I have the state, yes, and imagine I measure the first system in a basis, with some measurement which has projection phi1, phi1 and phi2, and some others. Yes. So for example, there is nothing, so there is 0, and for example, I measure my system in this basis. Okay. So let us think what will be. So imagine that I measure my state in this basis, and I obtain the result phi1. What will be what I know about the state of my second system? So first, what will be the result of my measurement? What will be the collapsed version of my state? Yep. So because I measured the result in phi1, what I obtain that this term dies. Yes, and I obtain that I know that my second system is in the state phi1. Yep. Oh, and okay, and if I measure it in the state phi2, yes, I know that what so this term would yes. So the result of the second, so I know the result of a measurement on the second particle. Of course, if it measures in the basis in this basis, let's say in high basis. Okay. This is the idea of entanglement. This idea also is story about correlations. Okay.
So does your definition depend on the basis you choose? Because, for example, in this basis it can be separate, but in other bases it can be entanglement.
Nope.
No.
Okay. Once again, so the entangle.
I think Schmidt rank is relevant.
It's yep.
It doesn't.
So your Schmidt rank is a
Okay.
So if you
and you say that your operators, well, your measurement operators are in Schmidt rank or what? Because they are, you choose like psi 1,
yes,
phi 1, phi 1. But if it was, I mean, the same, but it's not phi 1, but any other C1, any other state, what will be the result of it?
So I use it in order to show that so the entangled state possesses some correlations. So if you measure in this like Schmidt basis, it's easier for you to observe these correlations.
Okay.
So because you can choose another basis where you do not observe your correlations. For example, so let us consider the maximal entangled state. So 0, 0 plus 1, 1. Yep. And imagine that the A system is measured in a basis 0, 1. Yes. And then if the first system is obtained in state 0, so the second system is also obtained in state 0. And if the first system is obtained in state 1, the second system is obtained in state 1. And then imagine that the second like person measure the obtained state in a basis plus minus. Yes, then he will obtain with a probability 1/2 plus and probability 1/2 minus both of the states. So there will be no correlations. Yes, it's the first point. The second point may be much more important than the story about correlations is the following: that the entangled states are states which cannot be prepared by what is called LOCC, local operations and classical communication. Yes, local operation and classical communication. So what does it mean? So imagine that we have two parties, Alice and Bob, and they can communicate with some classical channel. Yes. And they have a number of different, let's say, coins or dices, whatever. And the idea is that they can, so we can say that A have some physical particles, and it can just make them in different states, and B have some different particles. Yes, and for example, A can toss a coin. Yes, and if coin is equal to 1, then they prepare a state like a spin in a state up. Yes, and she phones Bob and say, okay, I have a coin in state 1, so please prepare your also like a spin 1/2 also in a state up. Yes, or if a coin is a state 0, yes, she says, Bob says, okay, let's prepare your state in state minus, state down. Yes, and I also prepare in state down. Yes. And then, so they repeat it several times. They obtain a number of the spins. So a number of spins on this side. Yes, a number of spins of this side. And then they can give the pairs of the states to some other observable, so to some other person. Yes, who does not know what were these coins here. Yes, and the idea is that the state will be correlated, of course. Yes. Because if so they give these particles to some person, yes, and for example, he measures the first particle and see that it is in state up. He say, okay, I know that the second particle is in state down. Yes, because they were prepared in such a way. However, the state will be not, it's not entangled. Yes, because if we consider it density matrix, so who can say what will be the density matrix of this state prepared in such a way? So again, Alice, like throw a coin. If the coin is in the state 1, he say, okay, I prepare my spin up, and say Bob that Bob, please prepare your state also in your spin in state 1 up. If coin gives you 0, then Alice prepares a state down and says Bob, prepare your particle state down. Yes, and they repeat it several times.
Up plus down down.
Yeah.
And 1 to square 2. Not square. No.
So actually the result will be the following. It will be 1/2 up plus 1/2 down. And this state will be not entangled. So it's very, very different from the state of like say plus 1 square root of 2 plus minus. So it's very, very different. And who can explain why it's different? Why this state psi is different from a mixed state, this one?
Just calculate C.
Side, it will not be the same, yeah?
Yeah, it will not the same. How can I check it experimentally? It's like a basis point of quantum cryptography. So how can I experimentally distinguish between this state? Okay.
Because there will be some non-diagonal.
Yes, and any ideas how to change? Yes, and let us think. Okay, So what should I do?
Plus.
Yeah. So actually, you can choose. You can move to a basis plus and minus. So if you move to a basis plus and minus, so you will see that the state will be plus minus. Okay, and if you change the basis of the first part of this mixed state, what you will obtain this like 1/4. Actually, boom. Huh? Yes. So I change my basis, and I obtain this. Like, so here I should write it. So I will obtain a number of terms. I would not like to write it, but so the idea is that there will be no correlations if I measure in a state in a basis plus and minus. So because if for example, so you obtain, so let's say the first obtain state 1 state up, and the second obtain also the state up. Yep. And if the first person measure it in the state in the basis plus minus, so it was a probability 1/2 it obtain plus, with a probability 1/2 it obtains minus, and here the second person also obtain plus or minus, but they both will obtain plus or minus independently with independent probabilities. Okay, so that is why the states are different. Well, that's it. So this is the like feature of entangled states. Yes, and the second important point is that if I consider my density, my mixed states, yes, or my entangled states, what I can say is that if my pure, it's important that it's pure, if my pure entangled state is entangled, yes, then its reduced matrix, it's mixed, yes, because if I have this Schmidt rank larger than 2, then what I will obtain, then so my reduced states will have at least 2 non-diagonal terms, or at least 2 non-zero diagonal terms, and you see that is why it's mixed. So if I consider the diagonal representation, diagonalized form, it always will have at least two non-diagonal, at least two non-zero elements. Yes, that is why it's mixed. Yes, and actually the mixedness, the measure of how your state is mixed, your reduced state is mixed, is a measure of your entanglement. So the more the reduced states are entangled, the more your reduced states are mixed, the more your pure state is entangled. Yes, and so it corresponds to the fact that what is called a maximally entangled state is a state where your reduced states are maximally mixed. That means that they are proportional to identity matrix. Yes. So for maximally mixed, for maximally entangled state psi, your reduced states are proportional to identity matrix. Yes, and for example, our Bell states, which we considered previously, they are what is called maximally entangled, again because their reduced states are proportional to identity matrix. Okay, so they are like maximally correlated in some sense. So these correlations imply some, let's say, chaoticness of your reduced states. Okay. So how much time do we have? 10 minutes. Okay. Well, so let us at least start this. So it's final, like a picture. On the one hand, it's quite simple, but my experience says that there are several times where, let's say, very experienced people who are doing some great physics, but not like quantum physics or even quantum physics, but not quantum information, they do not understand these simple things, and they just have some misunderstandings. Okay, so we have two ways how to classify our states. So the first way, we can say that there are pure states, there are mixed states, the first way. On the other hand, we have the separable states and entangled states. And the basic message is that these two classifications is like orthogonal to each other. Yes, so it's different stories. And here I would like to consider all four variants of these two classifications. So the first is the case where the state is pure and separable. So pure and separable means that our Schmidt rank is equal to 1. Yes, and it means that so it's another way to say that my state is factorizable. Yes, so my vector can be I can consider my vector as a tensor product of two vectors which lives in the corresponding spaces. Yes. And if I consider not state vector, but it's but my density matrix, the story is the same. So my density matrix of my whole state can be considered as a tensor product of density matrices, which corresponds to each of the systems. Yes. So it's the most simple story.
So here the pure is corresponding to the A and B space.
Pure here corresponds, let's say, first of all, it corresponds to this psi, to the whole space, to the whole state. But actually, it appears that in the case of pure separable states, your reduced states, which are given by this row A and row B, they also pure. Yes, so they all are pure. The second story is about pure entangled states. So this is a story where the whole system is pure. It can be represented as a vector, but the number of coefficients in Schmidt decomposition is larger than 1. Yes. So we have at least two. It's at least two terms in this Schmidt decomposition. Yes. So again, remember. So this decomposition implies that we have these vectors which lives in different spaces, and they are orthogonal to each other. Yes. And what we have here, that the full space, the full vector, so the full state is pure, but if I consider its reduced state, they are mixed. And sometimes people miss it. Yes. So again, the full space, the full state entangled is pure. If and only if it's reduced mate, if reduced, okay, the pure state is entangled. If and only if it reduced states of this pure states are mixed. Yes. And again, so the mixedness of this pure states is a measure of the entangled. Yes. If it is not mixed, then we come back to the previous story. Then the third option is a mixed state but separable. It's a bit more like sophisticated. So the mixed separable state is a state which can be obtained as a sum of these terms. So what we have here? Here I have this coefficients pi. It's like a weight coefficients. So it's just probabilities. Yes. So we have some probabilities which sums into 1 and which are greater than 0. Yes. And for each of these probabilities, I construct a state which is factorizable. And here so you see that so here I have a tensor product of two density matrices. Each of them can be mixed. Yes. But so the most important is that they are factorizable. So they obtained by.
So if you have them mixed, you said just before that if and only if they are mixed, then they're entangled. So
No.
But wait a minute. So here I have a mixed state here. Yes. And there I have a pure state. It's very important. Okay. So here I have some mixed state which is obtained as a mixture of factorizable states, let's say, but not factorizable. So here I have factorizable states but pure. So I have pure 1, pure 2, and factorization. And here I can have not pure but mixed. So I take some mixed here, take some mixed here, put it in some mixture with some probability. Then again, put some mixed here, put it in my.
So I can have mixed A mixed B and get a pure, and get pure state and get mixed state. And if it's pure, it's entangled. If it's mixed, it can be entangled or not.
So actually, the idea is that you cannot obtain a pure state psi, for example, in this form. So the idea is that actually
it's mixed.
Yes, so it can be done. So you can.
For pure, it can.
Well, so here, so we know that rho A and rho B, yes, they are mixed, but it does not imply that you can write it like here.
Mm-hmm.
Yes.
But if we can, it should be entangled.
If we can, so
that's the case of the pure and entangled.
So here it's pure separable. So if we can write it like here, it's pure separable. Or I do not understand you.
It was an example of how to construct pure state using two mixed states. It's like you have mixed states A and B with density matrices, and then you just voila.
So I can get mixed. I can get mixed and separable, and then pure and entangled. It looks like that.
Out of two mixed states, you can create a pure entangled state, right? And
sorry. Once again, the previous point. Out of.
I don't think it's either one or another.
So here in this table, there's two boxes where I get two entangled subspaces. So pure entangled and mixed separable.
Yeah.
So here rho A and rho B in both these cases could be
mixed. Okay.
So,
yes.
And if I have to mix, I can calculate it this way and see it can be both and that. And
yes.
that.
Yes. So again, so for example, so remember this example. Yes. So in these two cases, in this case, for example, in the case of this matrix, your reduced state will be diagonal. So it will have this form. Yes. And in this one, also the same story. So they have the same reduced states, yes? But nevertheless, they're different. Okay. So if I can decompose my state in such a way, yes, then I obtain so this state is called mixed separable state. Yes. And the story is that if I consider a mixture of two mixed separable states, or just separable states, I also obtain a separable state. Yes. So again, so I take one separable, the other separable, consider it mixture, it's also separable mixed state. Yes. So that is why people say that the state of all separable states, pure and mixed, they what is called convex. Yes. Because if I take two states, so any of states which is obtained like on this line which connects these 2 points, they also are mixed. Yes. Well, and final story is about what is called mixed entangled states, and it's the most non-trivial one. It's a story when I have some density matrix rho, but I cannot find such rho A and rho B, which should be states with non-negative with trace 1, and cannot find these PIs in such a way that they will give me my density matrix rho. And it's the most complicated state, the most complicated case, because it's hard to prove that it cannot not be done. So, for example, you obtain some density matrix, and you look at this density matrix and say, okay, I don't know. So maybe there are some coefficients, some states which can be decomposed in such a way. Maybe not. Yes. And actually, it's proven that in some cases it's a hard problem to distinguish the state, to say if the state is entangled or not from density matrix. And what people can do, they can introduce what is called entanglement witnesses, which is like sufficient criteria that your state is entangled. So imagine, so you have this full space of your states. There is a set of separable states, and you can consider like a plane, yes. And if your state is, and you can find out either your state is on this side of this plane or somewhere on this side of your plane, yes. And if you find your state in the right hand side of your plane, then you say, okay, I know the state is entangled. Yes. However, if you find your state on the left side of your plane, then you say, I don't know. It may be separable or maybe entangled. And so what we know, that there are necessary and sufficient conditions only for two by two cases. It's let's say two qubit case. We will consider it further. It's what is called concurrence. And also there is a necessary and sufficient condition for 3 by 2 cases, as well as negativity. And it relates to what is called partial transpose criteria. And it works either for 2 by 2 systems and 3 by 2 systems. And also we can apply this negativity for other dimensions, but however, it will give you only the sufficient condition. So if you calculate negativity for your state and obtain it's like larger than 0, you say, okay, I know the state is entangled. But if it's equal to 0, you say, okay, I don't know, maybe it's entangled, maybe not. So this is the whole picture, but we will consider it in more details first. All the story about witnesses. So it's just general pictures that there are all possible combinations between mixedness and entanglement. It's very important because sometimes people miss this. Okay, any questions on this stuff? What's clear, not clear? What you can say? Is it easy? Not easy?
It was good.
Huh?
I think the table was good.
Table was good. Okay. So I hope that now it's
Around a month ago, I had a huge problem with this, as you may remember.
Okay. Yes. So this is. Yeah. different states. Yes. So nonetheless, so if you have some questions, you can always ask me. Okay, well, so I think it's nice to stop here. Cool, thank you. See you later. Да, я, по-моему, уже пропустил доклад.
Записывал.
А,
Сказали, лекция